So on Wednesday, I will be going online at 5:30. I'll stay online for as long as there's anybody around still asking questions. But primarily, I'll be answering questions that have been posted to the discussions board about any of the material that's on the exam, or questions about the exam, and so on and so forth. The exam is going to be available tomorrow night, but it will you will have only one opportunity to take the exam. However, it is not timed. So that means you can start the exam, you can pause, go off, you can close, so let's save your answers, go off and come back to the exam. But as long as you don't hit submit, you will be able to go back to the exam. And then when you finally hit submit, you will have submitted your answers. So you'll have to live with the result, I guess. So I think that'll help out. You have until Friday, end of day, midnight, in other words, to submit the exam. I'm hoping that you'll be sensible and not wait until the last minute to submit the exam. Also, if you have a project, now projects and the remaining assignments, I'll need a little bit more time to grade those. So the end date for any homeworks that you want to go back and redo, or for a project, if you want to submit a project instead of doing the exam, will be Thursday night at midnight. So for homeworks and a project, if you choose that route, Thursday night at midnight. For the exam itself, Friday night at midnight. Okay, so any questions on that? Last day to resubmit all homeworks, Thursday night at midnight. Any other questions? I guess not, because I don't see any coming up here. I just want to wait a moment because I know for some of you, there's a lag over the internet, depending on what your connection speed is. Okay, so let's move on. Okay, so the first thing I want to cover is what we've learned this semester, and what are some of the things that we should try to remember, try to like really wrap our heads around and remember as we move on to other courses, especially as we move on to EPI courses or courses where we'll be doing research and having to deal with data and so on and so forth. So when we started the semester, we started by trying to understand the idea of the different forms of data. What kind of forms does data take? Okay, so for instance, we basically limited that, especially with SPSS, to 3 basic forms of data. Okay, in other words, nominal data, which is descriptive or categorical, so on and so forth data. So nominal data, scalar data, as I'm using the terms that SPSS uses for them, which is numerical data, which is anything that's on any kind of scale, okay, and ordinal data. Now, ordinal data is basically a form of nominal data. Okay, ordinal data is not names or numbers or names or values or things or words that, in addition to being names, also have some order. So, for instance, something like egg sizes, for instance, large. Right? They don't sell small, do they? I don't think they ever sell small. Large, extra large, jumbo, and super jumbo. I guess there is a super jumbo. I have no idea. Those are nominal values. Large, extra large, jumbo, super jumbo. Those are names. However, the names have certain values. Now, is the difference between a extra large and a jumbo the same as the difference between a large and an extra large? Well, probably isn't, right? We don't know what it is. There probably is some standard or something like that. Actually, it might not even be that simple. Large may be a range, like 100 grams to 150 grams, and extra large could be 151 to 200. So in other words, something that's classified large could be 149, could be, and so on. But it's a name. We know it's smaller than extra large, which is smaller than jumbo, which is smaller than super jumbo. So they have order. Okay, but they're not the same as a scalar value or numerical value. Okay, and a numerical value, when we say 50, 60, and 70, the difference between 50 and 60 is exactly the same distance between 60 and 70. We know that that scale has a consistent value system, okay, over a long range of numbers. Okay, so nominal, again, is just names and they have no order. So for instance, could be something like hair color or something, or hair color, gender, right, and so on and so forth. Now, one of the other things that may come up when we talk about scalar values, numerical or scalar values, is that we can have discrete scalar values. And discrete are basically what we're referring to as things that are counted. In other words, they're integer values. They're things that you would count. How many eggs in that carton? It does 12. How many siblings do you have? 3, 4, 9, 6, and so on and so forth. So the importance here is that each one of these different types of data, particularly these three groups, nominal, scalar, and ordinal, we analyze them. We do statistical tests on them. We draw inferences from them using different methods. That's why it's so important to understand these different data types. As you move forward, as you put together a survey, as you create a study, and perhaps in your next course or the one after that, or for your capstone or your thesis, you're going to do some research, you're going to put together a study. You're going to want to keep in mind, what kind of data am I collecting? And at the end of the road, here's the road here. Yeah, here's the road. It's a winding, long and winding road. I think that's the Beatles, right? Long and winding road. So it's a long and winding road, right? And at the end of the road here, right, when you've collected all your data and now you have to go in here and you have to do your statistical analysis, whatever that might be, right, and so on, whatever it winds up being. When you have to do your statistical analysis, you've done all this work up to this point, right? You want to make sure that the data you wind up with is something that you know how to interpret, how you know how to perform statistical tests that'll give you, or ways to organize the data or perform statistical tests or do inferences that will be useful to you. And the best way to figure that out is back here at the beginning of the road when you are creating your survey, when you are putting together your study and deciding what data you're going to collect, how much data you're going to collect, and so on and so forth. So think about that at the beginning rather than at the end. I get many students that collect all sorts of data in a study that call me up and they say, well, I've got all this data, but I'm not sure what to do with it now. Well, the thing to think about would have been back here in the beginning is when you think about what you're going to wind up doing it with it after you've collected it all. But this is a starter. This is the important part here, is understand the data types that you're working with and the statistical test that goes with them. Okay, so now, then we moved on, and we moved on to probability and logic. Okay, and logic, we learned about Venn diagrams and so on and so forth. And these Venn diagrams were useful to us because they helped us understand certain situations where probability came into play. So for instance, this might represent group A and this might represent group B. Perhaps A is people who have cancer, and B is people who have heart disease. And we'll see that the people that are within, and this is the rest of the population here, right? Perhaps, well, all these people have heart disease, all these people have cancer, but there are some people that have both heart disease and cancer. At the same time, we could be interested in knowing what people have heart disease, cancer, but do not have heart disease. Okay, so a lot of ways for us to look at probabilities in terms of the area that this represents and the areas that were represented in here. And we learned our various formulas for our Venn diagrams. Okay, but the important thing is that was an introduction to probability, where we learned how to consider what the probability of an event occurring. So for instance, if we sampled 1,000 random individuals in nursing homes. We wanted to know what the prevalence of diabetes was in those nursing homes. Well, we tested 1,000 residents, and we decided 100 of them are diabetic, are positive for diabetes. Well, then the prevalence is 100 out of 1,000, right? Or in other words, 10%, which also tells us that that's PCAP, right? That's the prevalence or the probability of being diabetic if you were in this sample. And that represents an estimate for P, which is the actual population probability that you might be pregnant, you might be diabetic in this population. So we could go back into that population, and any individual in that, we might guess that the probability for that individual being diabetic is 10%. Okay, so this is our population parameter, and this is our statistic for our sample. And we learned that when we have a logical or dichotomous variable like diabetic or not diabetic, we're dealing with a proportion, right? 100 out of 1,000, for instance. On the other hand, when we're dealing with a numerical variable, then the statistics that we're working with to summarize the nature of all of the numerical values that might be represented in the population. So let's say we have population here. Here's our population. Out of that population, we sample 5 people. And those 5 people, let's say we're interested in their weights. Those 5 people have weights of 120, 140, 160, 150, 110. Right? Well, what can we deduce from that? Well, first of all, number one, we see that these numbers have a middle and they have a range, right? We have the lowest values of 110, the highest values 160. And we see that there's a middle here. And the middle value looks like it's going to be probably, I'm guessing 140, right? And that, so we have a description of this sample that tells us the median of the sample. It tells us the range of the sample. But now we can also go a little further and get the arithmetic average or the mean of the sample. And we can also look at the variability of the sample. We can look at it from the perspective of range, but we can also calculate a variance and a standard deviation. Remember, the standard deviation is the square root of the variance. We can calculate a standard deviation. These describe for us the middle of the values for this numerical variable, weight, which happens to be weight in this sample, right? But it only describes it for the sample. So we term the mean X bar. We term the standard deviation, say S, okay? But these estimate the values in the population. So the standard deviation, the variability of the sample, mimics the variability of the population. The mean of the sample mimics the mean of the population. The population mean, however, is mu and sigma, and for the standard deviation of the population, right? Often we'll never know these values, right? So, but we have a different method of organizing and understanding the data than we do for dichotomous variables like proportions. And then finally, we have these categorical variables. And with categorical variables, well, we have a whole nother way of dealing with them, which we just learned about. Okay, and one of the ways that we deal with them is we deal with them by organizing them in contingency tables. So we know that if you have a driver's license or you don't have a driver's license, right? What's the probability that you are? Oh, excuse me. Let's try this. Let's say if you're male or female, what's the probability that you have a driver's license or probability that you don't have a driver's license, right? Is there an association between being male or female, having driver's license, and not having a driver's license? Well, gee, that's pretty interesting stuff there. But now, male and female, that's a categorical variable. Driver's license is yes or no. That's a categorical variable as well. By organizing it into these crosstabs or contingency tables, it allows us to use statistics, chi-square statistic, for instance, use the odds ratio to determine whether there is an association between these variables and to quantify that association between those two variables. Okay, so we learned how to do that. Now, as far as looking at the means are concerned, we also had a mechanism where we were dealing with a numerical variable and a categorical variable. Well, gee, categorical variable, let's say it has two categories, like male and female, that categorical variable. And now we're looking at weights of males and female. So for each person in this sample, we have a weight, whether they're male or female. But now we want to see for ourselves, is there a difference in the average weight in this population for males and between males and females? Okay, that's pretty likely to be true, right? So we have tools now that allow us to estimate, to take the mean weight for females and the mean weight for males, and to determine whether they are different at a certain level of confidence for us, right? And we learned that a couple of ways to do that. One of them is we use confidence intervals, and the other one is we use something called a t-test, right? And the t-test allowed us to determine what level of certainty we have based on our sample. What level of certainty do we have that males or females have different average weights? Okay, so, and that's based on the variability and the averages and the sample size and so on and so forth. And we even took that one step further. What about when we have a numerical variable and we're associating it with a categorical variable that has more than two values? So for instance, perhaps we want to know what the IQ level is for people who have different color hair, right? Hair color, right? Okay, so we can take a sample of 100 people, let's say, or sample size of 100 people, right? And we can then take a look at, well, let's see, we have people with blonde hair, we have people with brown hair, we have people with red hair, and so on and so forth. And we can, if we apply a test to them and we get an IQ measurement, 110, 111, 103, and so on and so forth, we can break that into three different groups and compare the averages for the three different groups. The only problem is that our t-test is designed for comparing two categories. We have three categories here. So we use another test called analysis of variance. So that's what we learned up until the point of this exam. Okay, so we have these tools. So when you guys have data later on, or if you're doing a project and you're looking at your own data, and you can examine what kind of variables you have to decide what kind of tests that you should apply. Chi-square, odds ratio, analysis, variance, t-tests, and so on and so forth. Okay, so let's look at what we have, what we've been looking at the last week or so. Last 2 weeks. Yeah, actually we have 2 sessions a week, so last week or so, really. Okay, so now, last couple of sessions anyway. So now we started to look at data that was organized differently. We started to look at data in which both variables that we want to see if there's an association in are numerical variables. Numerical and numerical variables. So for each individual that we sample, for each subject number 1, number 2, number 3, number 4, there is a value for the first variable. Let's say that it's IQ. And there is a subject for the second variable. Let's say that it's BMI, right? Okay, so I'm making this up as I go along. So let's say for each subject, we measure these two values. 110, 25, 120, 32, 150, 24, 115, 27, and so on and so forth. And we want to see, is there an association between BMI and IQ? Okay, well, for each subject, we have two values, two numerical values. Okay, so literally we could say to ourselves, well, when BMI is 25 for this person, the IQ is equal to 110, and so on and so forth. And we can plot that on a graph, an XY coordinate graph, okay? And we can call X our independent variable, our predictor variable or independent variable, right? We can call Y our dependent variable, the value that's predicted by the independent variable. Okay, and we can actually plot this. So in other words, so I'm thinking that BMI might predict IQ, let's say. So we're going to put BMI down here. Okay, and let's say that this is 20, 25, 30, 35. And let's say this one, this individual is 25 and 110. So this is uh, uh, 90, 100, 110, 120, 130. Okay, so this individual would be plotted as a BMI of 25 and an IQ of 110. Okay, and how about this one? 32 and an IQ of 120 over here. So perhaps when we've plotted all these individual values, we see that there is an association. Now, this, of course, this is a ridiculous example, but we see, hi, how you doing? We see that there is an association between these two variables. Okay. So I am going to draw a best fit line between these two. Can anybody remember that? Can anybody tell me how I created that best fit line? What does that best fit line really represent? I'm going to mute my microphone for a second while I give somebody a chance to answer that. I have something I have to take care of over. Thank you, Yulia. That's very close. The best fit line takes each one of the values between the differences. This is called the error or this difference here is the difference between what it would have been on how far it is, how far the line is from that particular value. So each one of these differences, right? If we take that, what we're after is we want to plot a line where those differences, the sum of all of those differences, is the smallest it can be. So if I drew this line all the way down here, then every one of these lines would be far away, right? So that would not work. So a line up here wouldn't work either. So this line works better. Well, that's it in concept. In reality, it's actually the square of these differences between the value, the location of that value, and how far it is from the line. So it's actually this impacts the position of the line a lot more than the ones that are closer to it, right? Because it's a big number, then you're going to square, big difference, you're going to square it. So it tends to pull it up more. But it only pulls it up so far because then it's got to balance all these, then these others below it get larger as you pull it up. So it's actually the square of all of these differences between what your line represents and what the actual values are. Right? So you want to minimize the sum of all of those squares. That's how they create that line of regression. Okay, so one of the ways we do this is that we check the correlation. We calculated the correlation, and the correlation calculated for us. The correlation told us how good this fit is, how good this line represents these values, and how good is the association between these two variables. Okay, so that's one of the things we want to calculate is a correlation. Okay, and that correlation is measured with a number called Pearson's R, or Pearson's rho. So it's rho for the population, it's R for the sample. So the R value is something we calculate based on that sample. Okay, so the values, anybody remember what the values that R can have are? I'm going to put you on mute again for a second while I take this to be able to. Okay, so I'm back again. Okay, so I didn't have any volunteers there, so the R value, right? The Pearson's R value can have a value from +1 to -1, with 0 representing a situation where there is no correlation, and +1 representing a perfect positive correlation. What's positive correlation? Positive correlation is when one value, the predictor variable, and goes up, the dependent variable also goes up. That's kind of what this line is doing. On the other hand, if we have a -1 correlation, that's a perfect negative correlation. So that would be when the predictor variable, right? This like BMI, when that goes up, the dependent variable goes down. So it would have a downward slope. And anything that's close to 0, right, has less of a less of a significant or good correlation or association with the with between the independent variable and the dependent variable. So we're looking for correlations that are closer to 1 or -1 than to 0. Okay, and again, 0 represents a negative correlation. Okay, so let's take a look at where we can go from there. Well, from there, from there, we can actually use that relationship. From there, we can actually use that relationship. And we can take that line that represents the best fit line, right? Here's our independent variable and our dependent variable, y and x, right? And we can, based on this line, we can assign it a formula, a straight line formula, which is basically y is equal to beta 0 plus beta 1 x, okay, where beta 0 represents the y-intercept, right? There's nothing else there. How do I know it's the y-intercept? Well, if I make x 0, the 0 is the value at the y-axis here. So if I make x, if I assign x the value is 0, this part drops out. So y is equal to whatever this number is. So that's literally the place where the line crosses the y-axis. Okay, so that's the y-intercept. And then the b times x, b represents the slope of this line. In other words, the change in y over the change in x. Okay, the relationship between how much x changes to how much y changes. Okay, so that value b1. So for instance, if this line had a slope of 1, in other words 1x, right? But a slope of 1, if x goes up 10, then the change in x is 10, then the change in y is also 10, right? So in other words, 10 over 10 is equal to 1. So this one over here, if I looked at this one over here, it looks to me like the change in x looks like 20, and the change in y looks like less, like maybe 10. So the slope of this line would be the change in y over the change in x, looks like it has a slope of 1/2. Okay, so that's how that ties, that's how that formula ties in here. So why is that formula important to us? Formula is important to us for a couple of reasons. Number one, it helps us to use the independent variable as a predictor for the dependent or the y variable. Okay, so for instance, if the y variable is blood pressure, and B0 is a constant, it's just some number, plus let's say that X is, what might be a predictor of blood pressure? Let's see, the amount of sugar, the amount of salt in your diet, salt consumption, right? So maybe we can predict blood pressure by some constant plus some number representing a slope times the salt consumption in grams per week or something like that, right? That would be very interesting if we could see that association between salt consumption and blood pressure and to quantify it that way. In other words, quantify it in a way that tells us, once we know what B1 is, quantify it in a way where B1 tells us that if we increase our salt consumption by 50 grams per day, that what effect is that going to have on our blood pressure? So in other words, we can predict what impact that an increase or a decrease in salt consumption might have on blood pressure in a human being, right? So makes sense, right? So this says something that might be valuable to us. Okay, so now I'm just very quickly, and I'll go back to this in just a little bit. Now, that's very nice that we can use linear regression to predict what the value of the y is based on what x is. And draw a nice line here as a predictor and have a slope. And, y is equal to beta 0 plus beta 1 x. By the way, I may be using these the same way the text is using them or not. If I reverse them, don't worry about that. Just remember that the number in front of the x is the slope, and the other number is a constant, which is the y-intercept. Okay, so we can have a formula like this, where we have a single predictor, single independent or predictor variable, which helps us predict what the dependent variable. So a moment ago, we were interested in predicting blood pressure. And we're predicting blood pressure by knowing salt consumption. Well, obviously, that's not the only predictor of high blood pressure. What else predicts high blood pressure? Well, how about age? Age also is something that is likely to be a predictor variable for blood pressure. What else might? How about BMI? Might be a predictor variable. How about amount of exercise that a person gets? That might be another predictor. Well, now it's nice that salt consumption has a relationship here, and that we can use that to understand what the relationship is between salt and blood pressure, salt consumption and blood pressure is. But now, if we want a better predictor, why not incorporate all of these variables that are also predictors for regression, for the value of blood pressure? So instead of saying y is equal to beta 0 plus beta 1x, right? Well, how about beta 1x? How about we also include, and say beta 1x is BMI, how about we also include salt consumption, beta 2x2, plus age, beta 3x3, plus exercise level, beta 4x4. So now we have all of these other variables that contribute to it, that can aid our formula, can help our formula to be a better predictor of the y value. That's called multiple regression. Now, again, you're not going to need this on the test, but we want you to be exposed to it. So you know what it is. You know what it is when you see it. That's a multiple regression. And what we're trying to do there is we're trying to take advantage of other variables and incorporate them into our formula to make that formula, that regression, a better predictor for us. Okay, there's a few things we have to be careful about. Like, for instance, one of the things I put in here was BMI, right? Let's say I also decided, let's put in height and weight. Well, wait a second. Height and weight are already part of, so that would be B5X and B6X, right? weight and height are already included in BMI. They don't really contribute anything. They are that's an example of what we call collinearity. They already are represented by another variable that we already got in our formula. So we don't want those. That's one of the things we got to be careful with. We don't want those things in there. And there's ways to perform tests when you perform your multiple regression to examine the data that you have collinearity. Okay, we're going to give at least one multiple regression a try, or actually I'm going to show you a video where they go through a couple of multiple regressions. So we're not going to have multiple regression. We're going to have simple linear regression. I have my handwriting, my tablet is weird today. We have to calibrate it. Simple linear regression. We're going to have correlation, and we're going to have chi-square and odds ratio on our test. So I'm going to go over examples of each one of those today as we move on. But first, I want to go to Blackboard. And let me go to our class. And I am going to ask you to play this video, multiple regression. It's one of Levi's videos. And I think you can afford to start at, start at about 3 minutes in. Okay, and I don't want to go through the whole thing. So let's see where he gets done with his first example here. Okay, he's still working on the book. Okay, let's go up to about 41 minutes or so. And in this example, what's happening in this example is Levi is looking at a set of data where he wants to predict the weight of a book based on two variables. Okay, and those two variables include the number of pages, right? Obviously, you would think that would probably impact the weight of the book, plus whether it's a hardcover or a soft cover book. Again, a couple of things that will predict, a couple of things that you would think would have an impact on the weight of a book overall. Now, notice something interesting. That means that we have two predictor variables, and we have one dependent variable, weight of the book. Okay, so what kind of regression is this? Since we have one dependent variable and two predictor variables, this is a multiple regression. But one of the things that is really interesting about this is that pages is a numerical variable. And whether the book has a hard cover or a soft cover is a categorical variable. So it is possible to, in multiple regressions, to have both numerical variables and categorical variables. Most of the time, you'll probably have all numerical variables in a multiple regression. But occasionally, you may have categorical variables as well, as in this case. So I'm going to play this here. Okay, I'm going to turn off recording because obviously we don't need to record this. Okay, so I'm going to turn off recording briefly, and I'm going to play it on my computer. And you can either watch it online, or it may be clearer and easier to watch it by opening this file, multiple regression in session 16. Okay, so I'm going to go ahead and start that at about, what did I say, about 2 minutes and 45 seconds, 3 minutes in. And I'll play it, but you're also welcome to play it on your own machines as well. Okay, in that sense, I'm going to go for about 40 minutes. I'm going to cut in at, let's see, it's almost 6:20, at 7 o'clock. So at 7 o'clock, we're going to come back. If you watch it separately, come back. We'll be back online at 7 o'clock. And I'm going to keep this going here as well.
That we just did. So this is an and shape the response and talk about regression for multiple data types with a continuous response variable. Especially reading multiple regression tables and analysis of variance tables.
Are you able to get on?
By the way, ANOVA tables are not just for
if you sync it with
ANOVA as we've learned them. They're very versatile. We can use them for all kinds of regression.
I don't think you don't have a speaker on.
I'll talk about collinearity and the adjustments to the R squared, the coefficient of determination that we covered last class.
This conference will now be recorded.
Okay, so I think you guys can hear me again. You can see my screen again. Let's talk about logistic regression. Okay, so relax. Don't have to worry about this. Just an introduction. So let's say that that we've been dealing with a dependent variable that typically is numerical. It's a number, right? We wanted to know, for instance, what the weight of books were in one example. We wanted to know, I don't know, someone's blood pressure was in another example. But that dependent variable, the output that we wanted, was a numerical variable. Well, what if we're dealing with a variable that we want to understand what predicts it? In other words, a response variable, let's say, or a dependent variable. What if our dependent variable is a categorical variable, or specifically a dichotomous categorical variable? Okay, well, what is that? That's a variable that has two values. For instance, maybe we're interested in knowing whether someone is diabetic or is not diabetic, right? So let's say that we want to interpret that based on what their fasting blood sugar is. Now, fasting blood sugar is a nice measure of how your body responds to how your insulin what your insulin sensitivity is, how your body responds to periods when you haven't had sugar for a while, and so on and so forth. And it's a pretty good predictor of whether you're diabetic or not. And it's usually kind of that base clearing method for testing for diabetes. Okay, but really they do more sophisticated. If your blood sugar level is high, they might do more stringent glucose tolerance tests to determine if you're really diabetic, right? They do that a little bit more involved test than that to determine if you're really diabetic. So that by itself is not something that decides whether you're diabetic or not, but it's a good screening tool, right? We like screening tools. We did a whole section there, which I didn't mention before, on diagnostic tests and on this idea of positive predictive value and certain kinds of probabilities, in other words, conditional probabilities in that case. Okay, let's take a look at this. What if we want to predict whether a person is diabetic based on his fasting blood sugar test? Well, let's say that we do that. Here's a graph. I'm going to put a graph up that represents people, individuals that took a fasting blood sugar test and the results of a more standard test for diabetes based on that blood sugar. Okay, so let's say that fasting blood sugar is 0, 50, 100, 150, 200, 250, and so on. Okay, well, if it's under 100, If it's down at 0 or 50 or something like that, it's under 100, it's unlikely that you're going to be diabetic, right? But then if it's over 150 or so, 200, well, it's very likely that you're going to be diabetic. So the value for diabetes is either a 1 or a 0. Either you're diabetic or you're not diabetic. And based on your blood sugar, well, if you have a very low fasting blood sugar, under 100, chances are you're not diabetic. If you have over 200, chances are you're really good that you are diabetic, or almost certainly a diabetic. But in between there, it's kind of no man's land, right? In other words, the higher it goes, the more likely you are to be diabetic. So at a certain level, right, you're going to be diabetic. Certain level here, you're not going to be diabetic. But in between those values represents a probability. In other words, this is 0 probability. This is a probability of 1. So if you have a blood sugar of, say, 150, there might be a 50% chance that you are diabetic. So what we want is, instead of our formula where we had y is equal to our intercept, our B0, our y-intercept, plus some value, which is a slope, times x. Well, this is no longer a straight line, is it? Right? We have a flat line here, and then we have a gradual increase and flattening out, and flat at the top here, and so on and so forth. It has a more of a logarithmic scale than anything. And in fact, the formula that we wind up using for this probability is the natural logarithm of the probability of being diabetic over 1 minus the probability of being diabetic. Probability that you're not diabetic, in other words. So what is this? This is our odds ratio, isn't it? Or our risk of being diabetic in a particular population. Our odds are our risk of being diabetic. And in fact, it's no longer just a simple linear relationship, but with that value, but it's a linear relationship with the natural logarithm of that value. So then that's going to be equal to some value plus a value for a slope for our blood sugar. Okay, where x is our blood sugar. So this formula predicts what the probability or odds of your being diabetic is. Okay, that is logistic regression. Okay, and why is it called logistic? Because this idea of being a 1 or a 0 is a logical operator, like true or false, or like if even in the computer, a logical operation in the computer is plus 5 volts or 0 volts or ground, right? Or yes or no, right? Those are logical operators, right? So that's why they call it the logistic regression. Okay, so in that case, what's the difference here between simple linear regression and logistic regression? Well, the main difference is that our response variable, the variable, our y, or the variable that we're predicting, is a logical operator, a probability, instead of being a number. Okay, so that's really the main difference between our linear regression and multiple regression and logistic regression, is the form that response variable or that dependent variable takes. It's a probability. And so what does this mean? That means that based on what your fasting blood sugar is, we can use our formula, our logistic regression formula, we can use it to predict the probability that you are diabetic. So instead of using the volume of the number of pages or the volume of a book to predict its weight, right, with the numerical variable to predict the numerical variable, we're using a numerical variable to predict a dichotomous or a probability variable, a probability, right? So that's really the main difference between simple linear regression and logistic regression. Well, guess what? You can also have more than one variable here, though. And some of those variables can be categorical. Maybe we want to add another variable for gender, Maybe we want to add another variable in order to make this a better predictor, another variable for BMI. Maybe we want to add another variable for so on and so forth. And all of these make this line a better predictor, this formula, a better predictor for your probability of being diabetic. Okay, and what do we call that? Well, that's a multiple logistic regression. So we have simple linear regression, we have multiple regression, we have logistic regression, and we have multiple logistic regression. That's as much as I think you guys really need to know about this at this stage. If you're really lucky, you'll go off and have a great career and never have to worry about logistic regression again. If you're unlucky, at least now you've left this class having some idea. You know, it's not really part of our curriculum. At least you've left this class having some idea of what this means, what logistic regression means. Okay, so and if you get into deep water on this, then you start to maybe look for a statistician to help you on dealing with how you're going to handle your data. Right? But again, you can plan that ahead again. Try and plan that out in advance rather than wait for the end of a study and so on. Okay, so you guys have a rough idea what I'm talking about when I say logistic regression? Are you awake? Have you come back? Are you part of our class again? I see you all online there. Okay, good. All right. So that's kind of a simple introduction to logistic regression. Now I do, just like we had, Levi goes into let me just go back on the blackboard again. At the point where I stopped this, which was about 34 minutes in, Levi goes into a second example of multiple linear regression here. He doesn't cover logistic regression here. He goes into another example of multiple linear regression here. If you want, you can go back and watch the second half of this video and you'll be able to see another example of this being worked out. In addition to that, if you go down here to class 13 recording from last semester, it's actually, I think it's even longer ago than that. If you click on that, it'll take you another presentation where a logistic regression is worked out using SPSS, actually performed using SPSS. And the variables that they're using here.
Let's turn our attention to logistic regression.
Yeah, let me see if I can't find the
regression model. Now, the same principles apply to regression models. Here are three examples.
Okay, we're talking about.
Now,
okay,
let me show that for low birth weight after accounting for
okay, they use in this video. They're using the North Carolina birth weight data set that we have, and they're looking to see whether smoking or weeks of gestation can predict whether a baby has a low birth weight or not. In that data set, there's a variable called low birth weight, which is 1s and 0s, yes or no, right? And smoking status in the mother and weeks of gestation are being used as predictor variables for whether the mother gives birth to a low birth weight baby. Well, she either does or doesn't, right? It's either a 1 or a 0. So the result of this logistic regression is a probability, the probability or the odds, in other words, the odds that a baby would be born in low birth weight if a mother, if it's born in a certain number of weeks and the mother's a smoker, for instance. Okay, so that's what we're doing here is we're using these two predictor variables to predict a probability of a child being a low birth weight baby. Right? So again, logistic regression, our response variable, our dependent variable is a probability. Right? So again, that's a logical operator. Okay, so if you get a chance, you can play that and actually see this whole operation being done in SPSS. I'm going to pause it here. Okay, so that's really basically kind of an introduction to the topics beyond correlation and simple linear regression. Okay, so but I want to quickly go over some examples of the kind of things that might wind up on the exam, for instance. So one of the things that we might be interested in on the exam, let me pull out let me go back on the blackboard and just see if I have a good data file I can use. Well, one of the types of tests we're going to be working with, we worked with for the exam, is chi-square, odds ratio, and relative risk. Okay, so let me get back here. Okay, let me see if I have a good. Okay. Actually, let me see if I can't find that. North Carolina. Birth weight. Okay, now I'm going to get this out of the way. I'm going to take this data set, move it up here, and open it up. I'm going to use a single data set to go through some examples of this. And we are recording, so you'll have this later on. Let's see if SPSS finally does open up here. Here it goes. Okay, here's our North Carolina births set. Okay, so let's take a look at some of the variables that we have here. Well, we have a categorical variable called marital status. I'm going to go to variable here. My marital status is, let's see, marital status is coded so that 1 is married and 2 is not married. Okay, and we also has a categorical variable called premature birth, the premature infant. Okay, and 0 was not premature, and 1 is the infant was premature. Okay, so let's take a look at what I can do with this. Okay, so those are both categorical variables. Categorical variables for whether the infant is premature, categorical variable for whether the mother was married. Okay, so let's take a look at those together. Well, before I do that, I want to do one other thing here. And that is, I'm going to write down what are my variables again? My variables are premature birth and marital status. Right? And this is yes or no, and this is yes or no. Right? Or 0. I think this one was 1 and 2, and this was 0 and 1. Okay, so I'm looking at these two, right? And what I want to know, is there an association between premature birth and marital status? Okay, now they're both categorical variables, and they happen to be dichotomous. 0, in other words, have 2 values. You can only have 2 values in this data set. Okay, sometimes other data set, marital status could have more than 2 values. It could be married, divorced, widowed, separated, single, etc. Could have more than 2 values. In this case, it's 2 values. So what statistical tests can I use to test for an association between these 2 categorical variables that each have 2 values? Somebody help me out with that. Thank you very much. Chi-square and odds ratio. Okay, so what am I going to do? Well, first of all, what is my null hypothesis? Let's assume for a second that I'm going to use chi-square. What is my null hypothesis for chi-square? What is my alternative hypothesis for chi-square? My null hypothesis is right. No association between premature birth and marital status. There's a null, there's nothing. There's no association. My alternative hypothesis is that there is an association. You would write this out a little bit more neatly. There is an association between marital status and premature birth. That's my null and alternative hypothesis. Well, since this is a 2x2 table, I can also do odds ratio and relative risk. Okay, so what will my null hypothesis be for odds ratio? Anyone who want to hazard a guess at that? What will my null hypothesis be? My odds ratio is equal to 1. Excellent. My odds ratio is equal to 1. In other words, the odds of being a premature birth is the same for both groups. The rate they're going to have premature birth is the same for married women and unmarried women. And my alternative hypothesis is my odds ratio is not equal to 1. And similarly for relative risk, my null hypothesis, my alternative hypothesis would be the relative risk is equal to 1 or the relative risk is not equal to 1. Okay, that's great. So we have a basis for all this now. Okay, so now I'm going to go back to SPSS, and I'm going to organize this data into a contingency table, a 2x2 table. It's up here a little bit more. I'm going to go back to the data view and notice that I got marital status and I got premature. There it is. Was premature, was not premature. I'm going to analyze. So where is contingency tables hidden? They're hidden under descriptive statistics. Analyze descriptive statistics, crosstabs. And I'm going to put the exposure in the rows and the outcome in the columns. So the exposure is marital status. We think marital status may impact this outcome of, in the columns, premature birth of an infant. Okay, so that's good. So I'm going to just go ahead and click OK. First, if I go into statistics, nothing's going to get calculated yet. If I go into cells, it's only going to give me my zero values. That's okay. Right now, I'm satisfied with that. So I'm going to click OK. Okay, and here are my observed values. Out of 537 women, 48 of them had a premature birth. And out of 263 not married women, 45 of them had a premature birth. Almost the same number of births, but fewer women. That's very interesting, right? I'm going to copy this table into my little chart here. Okay, if I can do it without messing things up here. Actually, I'm going to open an Excel file. Okay, and I'm going to make this bigger. I'm going to make the same table here in Excel. Okay, and let's go move down a little bit here. And I'm going to say married, unmarried. And over here on the top, I'm going to put, I'm going to switch the rows around. I'm going to put premature. And here I'm going to put not premature. Okay, and premature was 48 for married and was 45 for unmarried and 489 for not married and 218. Did I get this right? I got it right? Okay, good. So I'm going to go over here. Okay, let me grab this. Let me grab it. Okay, so I'm going to add these up. Okay. Oops. I'm going to put an equal sign in front of there. You can just copy the numbers off the table if you wanted to. I know I did it the reverse way, but it doesn't really matter, does it? Oops. The trackpad's not cooperating, that's why this is so clumsy. Okay, I think we got it now. Okay, so here are my main numbers here. I'm gonna just kind of highlight those. Where is my, let me go to home. And it's gonna draw a box around them. Okay, so there are my main numbers. So now, if I wanted to calculate my relative risk, how would I calculate my relative risk here? Okay, this is totals. Okay, how would I calculate my relative risk? Well, for married women, the risk is 48 babies out of 537 births. So if I were to call this A, B, C, D, that would be A over A plus B, right? A over the sum of these to 537, the total 537. And what's the risk? So it's about 9% for married women. What's the risk for unmarried women? I use risk and rate at the same way. What's the risk or rate for unmarried women? Well, it's 45 over the total number of women, which is 263. Oh my goodness, look, their rate is higher than for unmarried women. Okay, so now I can calculate a risk ratio. Okay, what's my risk ratio going to be? It's going to be the risk that we have for married women over the risk that we have for unmarried women. So unmarried women are going to be at 52% less risk of having a premature baby than married women are. I could have also done it this way. Could have said, what's the risk for unmarried women? 17 over 8%. They're at almost double the risk rate or risk for married women. I could have done it either way, okay? But that's my relative risk. Now, my relative risk I can see being married is protective. Being unmarried puts you at risk, a greater risk, almost double the risk, 1.9 times as much risk of having a premature baby. However, that's not enough for me to say that that's a true association and it's not due to chance. What else do I have to know in order to say with 95% certainty or less than 5% chance of being wrong that this is really not equal to 1? In other words, the relative risk is not equal to 1 in these two cases. What do I need to know in order to say that? I need to know the 95% confidence interval for the relative risk for that number. We're not going to calculate it here. Excellent, great confidence interval. We're not going to calculate it here. Okay, we're going to calculate it in SPSS. But we've calculated now, that's the relative, these two are the relative risk, right? You can express it either way, but this is if this is married, shows the protective likelihood for married women. This shows the greater risk for unmarried women. It's just a matter of which one I put on top. Okay, so what about odds ratio? How do we calculate the odds ratio? Well, the odds ratio is equal to not 48 over 537, but the number of premature births over the number of non-premature births for married women. And for unmarried women, it's the number of premature births over not the totals, but the number of non-premature births for unmarried women. And then our odds ratio would be equal to 0.9 over 0.2, okay, which is point for notice. It's similar, not exactly the same. Or if I did it this way, it would be 2.1, okay? And that is our odds ratio. Okay, and again, that's nice that we know that, but we haven't proved that it's different than 1 yet. Okay, so that's good enough. We know what our null and alternative hypothesis would be for odds ratio for relative risk. But now, what about there's another formula, another statistic I can use for showing whether or not there is an association between marital status and premature births. What's that other statistic? What's the only one I haven't done yet? Chi-square. And how do I do chi-square? In order to do chi-square, these are my observed values. What do I need to know in order to do chi-square? I need to know my expected values. And I'm going to calculate those now. Okay, so let's calculate those. So let's see, married, unmarried, and actually I should have moved these down a little bit. Okay, and this is going to be premature. This is not premature. Okay, good. So it's going to add up to 800 just like before. This is going to be 537 because we didn't change whether we're married or unmarried. But we're gonna take a look at how would this be distributed if we use the totals here. This is 93 and this is 707. Okay, totals stay the same. Okay, so now if I wanted to know what's the rate, let's assume for a moment our null hypothesis is true, and there's no difference between the rate of premature births for married and unmarried women, right? What would be the prevalence in this population if that were true? The prevalence is going to be the number of overall premature births over the overall total population, right? That 93 is for the entire population. So this entire population, that are represented by this sample of 800 women, right? The rate at which we have premature births is 11.5% roughly, right? So now, if there's no difference between married and unmarried, we would expect both of these groups to have 11% premature births, right? So in other words, for the married women, we would expect that there would be 537 times 11%. We would expect 62 premature births. What about for the unmarried women? We would expect the same thing. We would expect out of those 263 women that 11.6% of them are going to be premature births, right? And this, if you look at it, it adds up to 93, right? So the total works out the same. So this is going to be just the difference between this and this, right? It's got to be. Okay, they all have to add up. This minus this. Okay, and again, this adds up to 707. Okay, so this is what we would have expected to see if everybody had a premature birth at the overall rate for the population of 11%. Okay, so if I gave you a problem with just the observed values, you would be able to create an expected values tree. Maybe, right? I'm hoping that you can, right? Or maybe you can go back at this video and look at this video again, see how I did it, and just really mimic what I've done. Okay, good. 93, good, excellent. Okay, so now I am going to now calculate my chi-square values. And if you recall, our chi-square values are going to be observed values minus the expected values squared divided by the expected values. Okay, and we're going to do that for each one of these 4 cells that we have here. If it had been a 2x6 table, we would have done it 12 times. 12 times 6, 2 times 6 times 12 times. So I'm going to do it 4 times for each of these. So it's going to be equal to, I'm going to do the first cell here. I'm going to do the 4 cells in the same position. So my observed values is 48 minus my expected value, which is 62. I'm going to put that into parentheses. I'm going to put a little up caret, which means square, and then a 2, which means square, and divided that by my expected values. Right? That's that one cell. I'm going to hit enter, and it calculated it for me. And then I'm going to do the same thing for the next cell. Observed value 45 minus 30 squared divided by 30. Okay, except I'm not going to bother to do it. I'm going to copy it by doing this, and it should mimic the calculations I just did, except move them down 1 cell. So this I'm hoping will work, and it looks like it did work. And now I'm going to go across, so I don't have to individually do this for every cell. There we go. Okay, so this is the calculation for each one, observed minus expected squared of expected value for each one of these cells. So now my chi-square value is equal to, remember it's that big summation sign, is equal to the sum of all of these. And that's equal to 11.6. 0.47. Now, how do I know if that chi-square is big enough for me to reject the null hypothesis that there's no association between these? Well, I have to go and look up the critical value of chi-square. Well, what is the critical value of chi-square? Well, first thing I need to know is the number of degrees of freedom. How many degrees of freedom do we have here? Okay, the degrees of freedom chi-square are the number of rows minus 1 times the number of columns minus 1. So 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1 degree of freedom. So if I go to look it up on the table, it comes out to, and I'm not going to split from the table right now, 3.84 is my critical value of chi-square. That's the value I need to exceed in order to reject the null hypothesis. Have I rejected it? Have I exceeded that value? Yeah, I have. I got a value of 11, which is bigger than the critical value. So I can reject the null hypothesis that there's no association between married women and marital status and premature birth, and accept the alternative hypothesis. There is an association between marital status and premature birth. Okay. So that's great. Now, what about odds ratio and relative risk? We calculated them, but we really need to know the confidence interval for the odds ratio and the relative risk to make sure that it's not equal to 1, right? To make sure that 1 is not inside the confidence interval. So if I go back to SPSS and to my variable view, there we go. Let me go to my variable view, my data view. Here's my data view. I'm going to go to Analyze again, Descriptive Statistics, crosstabs, except this time I am going to select cells. Okay, well, I already have them, so I'm not going to bother with that. I'm going to select statistic and say, give me the chi-square statistic and give me the risk, the relative risk and odds ratio. That's what that's going to give me. And I'm going to go into cells here, and I'm going to give me the expected values. And I'll click continue. Then I'll click OK. Okay, so let's see what my result is. Well, look, my result is 11.457 for my chi-square value. Let me get back here. Where'd I do it? There we go. 11.447 I got. So pretty close. Oh, exactly, basically the same thing, right? We calculate the same way, right? So chi-square is 11.475. They rounded it. Okay, 1 degree of freedom, just as we said. And in this case, we could either look up and see that, in fact, this exceeds the critical value for 1 degree of freedom, or we can just rely on the next column, which is the significance of the p-value. So having a big enough chi-square value to reject the null hypothesis is the same thing as having a significance that's less than 0.05, less than 5% chance of getting this big a value like this and being wrong if we reject the null hypothesis, right? So since this is less than 0.05, I don't have to go look up the critical value with SPSS. It gives me this, and it's less than 0.05, so I can reject the null hypothesis that there's no association, except the alternative that there is an association. Okay, well, okay, great. That's terrific. How about our risk estimates? Remember our odds ratio came out to be 2.1, right? Odds ratio. Well, look, we have a confidence interval, 95% confidence interval for our odds ratio, which is 1.336 and 3.3. Let's say 1.4 to 3.3, right? Is 1 between those two. So we're 95% sure that it's not 1, right? So we can say that our odds ratio is 2.103 with confidence interval of 1.359 to 3.255, which excludes 1. So our odds ratio is not equal to 1. So we can reject the null hypothesis, the odds ratio is equal to 1, and accept the alternative hypothesis that the odds ratio is not equal to 1, which means that there is some association between yes. And not only that, it also tells us that women who are unmarried have 2.1 times the odds of having a premature baby than women who are married. And the next column down here is our relative risk. Our relative risk is 1.1, okay, which is not as dramatic as the other one is. But we call it premature infant. Odds ratio, risk. Oh no, here it is down here. This is our odds ratio for premature birth, which is 0.522, which is women who are married have 50% of the probability, 52% of the probability of premature birth that unmarried have. And again, it excludes 1 for the relative risk as well. Okay, so we want to make sure 1 is not between these numbers for the confidence interval. If you don't see 1 between these two numbers, you can reject the null hypothesis. I'm not sure about this one. Why did this one come out so small? Cohort premature. 0.52. This should have been the inverse of this. So this should have been 1.9. I'm not sure why it did that. Risk estimate. I have to take a closer look at that. But but at any rate, in any case, you're going to come up with the same conclusion that for both odds ratio and relative risk, you can reject the null hypothesis. Okay, so notice the other thing here. The other thing was that you can use this to check your calculations in Excel. Not only that, but let's say that part of a problem asks you to if you had both data sets, Excel and SPSS, and you had trouble calculating your expected values, right? Look, SPSS gave you the expected values here. So you can use SPSS to check your work. You can use Excel to check your SPSS work and the SPSS work to check your Excel work. So there we go. There's that whole test out of the way. Now, there might be a couple of short answers that you might have to go back and look at a PowerPoint or maybe read something in the book, like look in the index and look up something in the book or something like that to answer, or use your memory or something. So there might be some short answers buried in there or something like that. But I mean, this is going to be one of the main problems on an exam like the final exam. Like I said again, you'll have plenty of time to do it, and you'll be able to pause, go, pick it up the next night, and so on and so forth. As long as you don't hit submit until you hit submit. Okay, so let's take a look at correlation. Okay, now, correlation, we're not going to look at multiple linear regression. We're not going to look at logistic regression for the exam. We're going to look at correlation, and we're going to look at simple linear regression. Okay, so let's take a look at something that we might be interested in. So we might be interested in 2 numerical variables to determine if there's an association. So let's see, we have the mother's age and we have the birth weight of the baby. What do you think? Do you think it's possible that there's an association between the mother's age and the birth weight of the baby? Possible. How about weeks of gestation and the birth weight of the baby? That sounds good, right? That sounds like a possibility. Those are both numerical variables. If I want to show an association between 2 numerical variables, what kind of test do I use? Right. 2 numerical variables, age and BMI or something like that, or age and blood sugar or something like that. We're going to use correlation. Anytime we have 2 numerical variables, think correlation. Okay, so we're looking for a correlation between weeks of gestation and the baby's birth weight. And thank you very much, guys. And weeks of gestation and ounces at birth weight. So let's see how I'm going to do. First thing I want to do is I want to examine this to see visually if I have an association there. So I'm going to go into graphs. And again, you guys can explore all these other options as well. Legacy dialogues, scatter dot, simple scatter dot. And I'm going to move in just to get into the habit now. I'm predicting that the weeks of gestation, where is it now? Completed weeks of gestation is going to be our predictor variable, and the weight of the child in ounces is going to be our dependent variable. Independent variable X and dependent variable Y. In other words, weeks of gestation predict the weight of the child in ounces. Now, for correlation, I didn't need to do this. I could have waited till regression. Correlation doesn't care, which one I put in the X and the Y. So I'm going to click OK, just looking for an association. Not worried about cause, but we might as well get into the habit of trying to identify which one we think is the independent variable, in other words, the predictor variable, and which one is the one that is being predicted. Like in this case, the predictor or independent variable completed weeks of gestation, and the predicted variable or the dependent variable is the weight of the child in ounces. So let's take a look at this graph, see what we see. Well, wow, sure does look like that, right? I mean, look at this, right? It looks like there is an association there. I'm not in love with the fact that it's so tight down here and so broad up there and so on, but it is what it is. So let's see if we can demonstrate a correlation here. So I'm going to go up to Analyze. I'm going to Correlate. And which of these am I going to choose? I'm going to choose bivariate, right? Because two variables. And I'm going to move the two variables in here. And notice that it doesn't ask you to separate them, right? Now, completed weeks of gestation, since correlation doesn't look at causality, it doesn't care which one you put in first, or it's just not going to let me hit OK until I have two of them in there. Completed weeks of gestation and weight of the child in ounces. And I'm going to click OK. Notice Pearson's correlation is already checked. I'm going to wait. Okay, click OK. And what is the correlation? The Pearson's correlation is equal to, okay, so what is this? Completed weeks of gestation, completed weeks of gestation. Well, that's one, it's the same variable. Completed weeks of gestation to move over to weight of the child. Well, the correlation between completed weeks and weight of the child is 0.583. Not bad, not great, but not bad, right? It's a pretty good predictor, right? So 0.583. So the significance, the probability that the null hypothesis is true, in other words, probability we would get this extreme of value if the null hypothesis is true, is less than 0.001. So our criteria for that is we want it to be less than 5%, right? So right away we can reject the null hypothesis. What is the null hypothesis for correlation? The null hypothesis for correlation is that there's no correlation between these two variables. And the alternative hypothesis is that there is a correlation. Okay, well, how would we write that? Well, remember, what does R have to be for no correlation? 0, right? Anything different than 0 is a correlation. 1 or -1 are really good correlations. Anything close to them, really good correlations, right? As the number gets bigger up to 1 or down to -1, okay? But 0 is no correlation at all. So our null hypothesis is that rho or R is equal to 0. And our alternative hypothesis is that rho or R is not equal to 0, right? So we can, given this result, we can reject our null hypothesis that R is equal to 0 and accept our alternative hypothesis that it's not equal to 0. And our estimate of it happens to be 0.583. Okay, so that's our correlation. Okay, so now let's go a step further. Let's try and use this correlation to create a formula that allows me to predict the weight of a child based on the weeks of gestation. So I'm going to go, that's called a regression, a simple linear regression. Analyze, and I'm going to go to, where is it, regression, linear. See, now I have to put in my variables, my independent and dependent variable. Well, my dependent variable is the weight of the child in ounces. Okay, so if it doesn't work, if you get results that don't make any sense, and you say, oh, what did I do wrong here? Go back and take a look. Maybe you reverse these two. right? So just as they were warning, because I noticed that come up on the homework, that a lot of people tried the homework like 5 times, they kept getting the wrong answer, and then suddenly they realized, oh, I had these variables reversed. You know, when I had to put them in 2 separate boxes, especially on the t-test. Okay, so independent variable, the predictor variable is the what was it again? It was the weeks of gestation. Completed weeks. Okay, so notice that there's space in here for more variables. Why do you think there's space over there for more variables? We can have 2, we can have 3, we can have 5. What is that called when we put more than one in there? That's called, no, this is by variable, what we're doing now, 2 variables. What if we put 4 or 5 of them in there? That's called multiple regression, right? Then what we're doing is we're using many independent variables to predict the dependent variable. That's how we do a multiple regression. Okay, so I'm just going to do this now, the completed weeks of gestation, and I am going to go ahead and ask it, okay, to go ahead and do that for me. Let's see what I wind up with. Well, here we go. Wind up with, here's our value for R, 0.583. It just recalculated it. Then it calculated a value for R squared. Also calculated something called adjusted R squared. It's almost the same thing as R. That takes into account the variable size, the sample size, some other factors, and adjust the R value to something that's more conservative. Okay, but you can use either one of those for our purposes. I would just stick with the R squared for our purposes. Okay, so at any rate, so you have R squared is 0.34, right? That's R, just R times itself, 0.34. So the correlation was 0.58. The R squared is 0.34. You know another name for that that variable? It's the coefficient. Anybody remember what that's called? The coefficient of. Anybody remember it? Determination, right? Coefficient of determination. What does that variable R squared represent? It represents, you're right about, you guys are right about that multiple. What does that represent? That represents the amount of variability in the deep independent variable, in the dependent variable, in the weight of the child that can be attributed to the weeks of gestation. So 34% of the variability in the birth weight of a child in this population can be attributed to the number of weeks of gestation. So that tells you, well, it's a pretty important factor, the weeks of gestation, right? So you want to make sure that you don't have premature births, right? But it also tells you something else. What else does it tell you? It tells you that 66% of the variability is due to other factors. And what are those other factors? Those other factors might be the marital status of the mother, smoking status of the mother, et cetera, et cetera, et cetera, right? So our R squared is 0.3. So let's go down here, and our analysis of variance, which was what we used for our significance, is 0.000. So it is a statistically significant result. So here are our coefficients for our formula. So our formula says that the slope for the weeks of gestation is 4.837, and our y-intercept is -70. So let me get a piece of paper up here. I'm going to call this 4.8, and I'm going to call this 70.4, negative 70.4. Oh, I should really start with a new piece of paper. So how am I going to apply those two numbers? Remember, my formula is y is equal to B0 plus B1x, where this is the slope and this is the y-intercept. Again, if they use different letters, don't worry about it. You'll recognize the same form in the formula. So y is equal to, what was it, -70 plus 70.4 plus, what was the other one? 4 point, I don't remember anymore. 4.8? Anybody remember? 4 point, I'm going to call it 4.8. Don't worry about it. Actually, well, let's just go with -70 of 4.8 times x. Well, what's y? Y is the weight of the infant is equal to minus 70 plus 4.8 times the weeks of gestation. Okay, so if I have a baby that is born at 30 weeks, what does this formula predict that its birth weight is going to be? The formula says, let's see, it's going to be minus 70 plus 4.8 times 30 is equal to, how much is that anyway? Let's see. We have a calculator. Okay, 4.8 times 30 equals this, minus 70. Okay, is 74 ounces. That baby, we predict that baby is going to weigh 74 ounces. Okay, so we have created a formula that predicts the weight of a baby. Is it going to be perfect? No, because remember, R squared was only equal to like 34%, right? So it's going to be a decent predictor, but not perfect, right? Okay, so that is our formula, our regression formula. Why is this slope so important? The slope is important because it tells you that if instead of being 30 weeks, it had been 31 weeks, how much more would that baby weigh? Take a look at the formula. If it had been 30 weeks, 31 weeks instead of 30, this would have been 30 or 31 times 4.8. It would have been 4.8 ounces more. What if it had been 40 weeks, 10 weeks? It would have been 48 ounces more, right? That's why that slope's so important, because that slope tells you the relationship between the predictor variable and the dependent variable, the predicted variable, right? That gives you that important relationship. So we know that, gee, we want to keep that baby going for another 10 weeks because we want it to have a decent birth weight, right? And this is how much, so can we, how about 35? Is 35 enough? Well, 35 would be about 25 ounces. It'll be 100 and whatever, 5 ounces or something like that. Maybe that's good enough. Maybe we can get to 35. That'll be enough. We'll deliver the baby, right? If it's a high-risk pregnancy. So that gives you an idea of where you're going to be at that number of weeks of pregnancy. Oh, it doesn't matter. That's just there. That's a placeholder, really, right? Because in other words, what does that mean? That means that, I didn't draw this very well. That means, yeah, here's my axis here. That means that if the slope is 4.8, it might look something like this, but that means that the y-intercept is going to be below here, below the x-axis. That's what that means. So that's just a placeholder for the line, because that's the weight of the baby when it's 0 weeks. Does that make any sense? There's no weight of the baby when it's 0 weeks. Baby's not born yet, and there's no baby yet for 0 weeks, right? So it doesn't make, so it just tells us, we know the slope is this much, but this line has the same slope. This line has the same slope. This line has the same slope, but only one of those lines goes through minus 70 on the axis. So we need that to draw this line, but it doesn't really tell us much about the relationship between the two variables. Okay, so, but it's still necessary, right? So this is great. Now, if we could just do this, we're in great shape for this. I just want to show you one other thing here, and that is I can also go back here, and I'm going to do something a little weird here. I'm going to go to Analyze, to Regression, Linear Regression, and I'm going to go into this, click this Save button. And I'm going to ask it to give me the unstandardized predicted values and the unstandardized residuals. Residuals, same thing as errors, right? Residuals are just the errors. Okay, so I'm going to click OK. Okay, so now notice, look, I got an extra box down here, but everything else seems pretty much the same. So what changed? If I go back to my data view, well, all of a sudden, there are 2 new columns, the predicted values and the residual values. The predicted values are, this is the, like, see this first one here, 123? That's 123 ounces. That is for that particular baby. This is what our formula predicted that that baby's weight would be. That's the predicted value. But now, since it's a real baby, we can go back and look at its actual weight. 111 ounces. Wow, we were pretty far off on that one. We were off by 12 ounces on that one. Well, how about the next one? Next one, we were off on the other side, 7 ounces. Next one, this one only 2 ounces. This one, 20 ounces. This one, 1 ounce. This one, 1 ounce. This one, less than an ounce, right? So some of them got pretty close on. These are the predicted values based on the formula, and these are this other column, residuals, are the error, the difference between what the baby actually was and what our formula said it was. Okay, there's reasons why we want to know that. I'm not going to cover that on the test. Reasons why we want to know about these residuals is because we want these residuals, these errors, we want them to be random. We don't want them to be systematic. Like for birth weight babies, they're all in low birth weight babies are all in one direction. They're all negative, and for high birth weight, they're all positive. We want them to be random. We want the errors to be random because we don't want some weird things going on in the background with the data that we're not aware of, right? But we're not going to worry. There's ways to predict how random they are here, to standardize them and to graph them and so on and so forth. We're not going to worry about that for the test. So if we can just do that for the test and answer some simple, do a calculation like predicting if this number of weeks and so on and so forth, or create these extra couple of columns and do our R-square calculation and create that formula, I think we're in pretty good shape for the test. Okay, so I think that's really where we want to be. Let me see what else I want to bring up. Oh, before we get done with this, I just wanted to bring up, just so you could see. I'm sorry I closed that. I didn't close it. Is it still there? Yeah, it's still there, I think. Yeah. Okay, I just wanted to do one other thing here. Analyze the descriptive statistics. Oh, now I'm going to go down to regression, linear regression. Okay, completed weeks of gestation. What else did we say was something that might influence the weight of the infant child? Well, the marital status of the mother. Well, how about the age of the mother? Put that in there. Smoking status. Let's put that in there. Let's put that in there. Now, enter. This thing, enter, is going to force SPSS to use all of these variables in the predictor variable. If I do stepwise instead, it's just kind of an extra detail. I could just do enter and force it to use all of these variables. If I do stepwise, what it will do is it will do a regression. It will do a correlation between the independent and each one of these independent and the dependent variable, and it's going to put the first number it's going to use is going to be the first part it's going to use is going to be the best predictor, and then the second the next one. And if it's not significant, statistically significant, it won't use it at all. If I use enter, it's going to use it, force it to use them all. If I use stepwise, it'll make its own judgment about this. I'm going to use stepwise for our argument's sake. I'm going to click OK. Let's see what we get. If I go down here to our coefficients, first of all, let's see what I got here. First of all, remember what our R-square was before? Yeah, hang on a second here. I can't find it here. Residual statistics. Okay, so for each of these different models, and each of the different models are, if it added in, if it used as a predictive variable for model A, it was predictive variable was just the completed weeks of gestation, right? In other words, what we originally started with, it was the R-square was 0.339. If we included the weeks of gestation and the age of the mother, the R-square was 0.364, a little bit better. If we included the weeks of gestation, the age of the mothers, and smoking during pregnancy, it was up to 0.37. And if we included all of these variables and marital status, it was up to 0.382. So we improved. Yeah, it would have been nice if we improved it more, but it didn't help that much, right? But you can see we got the formula that we wound up with, which is represented by all of these coefficients. You know, x, each one of these goes in from another x. It's additive. It's going to be minus 70 plus minus 84 times, minus 4.83 times the weeks of gestation, plus 4.8 times the weeks of gestation, plus 0.57 times the mother's age, plus 4.75 minus 6.54 times the smoking status, which is 1 or 0, right? And so on and so forth. If you made a formula out of all of those, then you managed to get your predictive value up to 38% from about 33%, right? Helped a bit. This example was not a great example of that, right? Sometimes it helps a lot. Right? So that is that basically is a very quick view of what a multiple regression would look like. We're adding in more variables, hoping to get a formula that's a better predictor than just using one variable. You don't have to worry about that. You're only going to use one variable for the exam. Okay, so I think that's enough for tonight. If you're up for it, play that logistic regression video and the rest of Levi's video, because he does another example on there. I think it'll, and if you want, you can wait until after the test is done, so you don't cloud your mind up with stuff you don't need right now, right? So I don't want you to fill your brains up, right? Although I don't think that's possible, right? I don't think that actually works that way, right? I think in the 60s, they had this thing that like you only use like 3% of your brain, and I think there was even a horror picture where somebody boosts his brain and now he's using 70% of his brain and he's like moving tables around and stuff like that. So but we used to have this axiom that you only use a small percentage of your brain cells or something like that. I think that's kind of gone. I don't think they look at it that way anymore. But yeah, you don't have to worry about the rest of this. They stick with the other stuff now. But I think you really should play those two videos at some point, just so you get a little bit more complete view of how you might actually do a multiple linear regression, and particularly logistic regression using SPSS. Okay, so I'll have the exam posted by tomorrow night. Try and get your homeworks in, and if you're going to do a project, get it in by Thursday at midnight for the assignments and the project, and then you'll have until Friday night at midnight to complete the exam. Submit the exam, although if you get it, I think most of you probably get it done well before that and be submitting it. And that's our semester. That's it. That's all she wrote. And you guys have done good work. I have to tell you that, like, for a summer class, you've kept up with, most of you have kept up very well with the yay. Don't sound that enthusiastic, please. You've kept up with the assignments and stuff like that pretty well, almost all of you. And I've had to do less begging and pleading and threatening this semester than most semesters. So I really appreciate that. So if I don't speak to you, if I don't see you online on Wednesday, and again, I'll just be online long enough to answer any questions and stuff like that. So figure 5:30 to 6:30 for sure, longer if there's a lot of questions and stuff. And please, if you have questions about the exams particularly, please post them on the discussions board. That way I can answer them there, and verbally as well on Wednesday. Answer them there so that everybody gets the same advantage of any responses I make, and may give her clarifications and so on and so forth. Okay, take care, guys, and I hope you have a great summer if I don't speak to you again.